Stony Brook University, despite the fact that there seems to be sort of a conspiracy of natural terrain features and infrastructure choices in this country to make that as hard as possible, given how close it is geographically. Before that, he was at TTI. Before that he was at Yahoo Research. Before that, he was at TTI. Before that, there were some other places, but ultimately a PhD at the University of Genoa. And Francesco is sort of one of the central figures at the intersection of machine learning and optimization. So please welcome him. Somewhere. Does it work? Can you hear me? Okay. Okay, good morning, everybody, and thanks for inviting me and give me the possibility to tell you something about my work. So before starting, let me first say that in this talk there is a little bit of everything. There is a little bit of optimization, a little bit of machine learning, a little bit of sequential investment and online learning. So I don't expect each one of you to be an expert on these topics. I am first not an expert on all these things. So if something is not clear, just stop me, okay? Okay, let's start. What's the motivation of all this? This is basically the motivation of everything I do in these days. I want machine learning to be completely automatic, because it's not. Currently, you always need a human that is doing something, that is looking at results and tweaking parameters on making critical decisions. So I would like machine learning to be completely free from hyperparameters. Learning rate, it's one of these hyperparameters, especially when we train deep networks, but I would like to remove all of them. So I don't want humans in the loop, and given that I am a theoretician, I would like some guarantees. If it is an optimization algorithm, I would like to guarantee that this algorithm will always converge, and not sometimes when I am lucky. So this is a brief outline of the talk. I will first introduce you the problem of optimization of non-smooth convex functions. And then I will tell you something about how I solve this problem, that is through a reduction to betting on a coin, and why this is a good idea and how things work. And finally, I'll show you some empirical results on deep networks. OK, let's start with the first part. Non-smooth convex optimization. So first, why I should care about optimization? Because I would say 90% of modern machine learning reduces to writing an objective function and minimizing it. This is what we do most of the time. So what does it look like? Basically, simplifying a lot the situation, you have a function, for example, this blue line here, and you want to find the minimizer that is this point here. Okay, so what are the algorithms that we typically use to minimize numerically a function? They are all based on some kind of gradient descent procedure. It can be stochastic, it can be a subgradient instead of a gradient, but the main message is always the same. You start from a point, for example, you start from w equal to 0. And then you evaluate the gradient on that point. Now, the gradient will basically tell you in which direction you should go in order to minimize the function. Okay? So what you do is that you jump a little bit in that direction by a quantity that is called learning rate in machine learning, or step size in optimization. That is just a number that tells you you should go in that direction by this amount. And you keep doing this until sooner or later you will arrive at the optimum. Now, the point is that these learning rates, I don't know how many of you are actually training deep networks. If you do, you will know that this is a critical parameter. And the reason is quite obvious. If the learning rate is too small, it will take forever to reach the optimum, just because you are jumping by quantity that is just too small each time. On the other hand, if the learning rate is too big, you will quickly arrive in the area of the optimum, but then you will never converge. So in this case, you will keep oscillating between these 2 points, and that's it. You will never converge. And the reason is that you cannot be more precise of something that is proportional to the learning rate, because you are jumping around of this quantity, so you cannot be more precise than that. Okay. So what's the current solution to this problem? typically people they just try all the possible learning rates, and they select the good ones. And this is not a very satisfying solution, of course. Now, another thing is that the graph that I showed you is just a very simplified situation, also because typically what we do is not gradient descent, but we use stochastic gradient descent. So we don't have the actual gradient of the function. We just have an estimate of the gradient that it's noisy. So just in expectation, that will tell us the right direction, but there is some noise on top. So a lot of things that you could think to do in the batch setting. So for example, you could say, OK, I know that that is the direction. I will just select the best step size in that direction. You can do that in the batch setting, but you cannot do that in the stochastic setting anymore because there is noise on top. So, but what about all this family of algorithms that are adaptive in some way? I mean, the first one was ADAGRAD, that stands for adaptive gradient. But we have a lot of them. They all have some ADA in the name somewhere. So let's look at the most famous one, and I would say also the most misunderstood one, that is ADAGRAD. What ADAGRAD would do in the same situation? So this is ADAGRAD. I don't know if you can see the green line. You still start from 0 with just random initial point. And then you still jump each time by a quantity that is your learning rate. The only difference with respect to before is that now the learning rate is going to 0 as 1 over square root of t. That's it. This is what ADAGRAD would do. And you can see that it's not particularly smart. So the only difference with respect to before is that now you have the guarantee that you will converge to the optimum, because sooner or later, the learning rate will become small enough that you will reach any precision you want. But you still are critically dependent on the initial step size. So you take that step size and then you keep decreasing it, but the final conversion will still depend on that initial choice. And so even in ADAGRAD, there is that small number that you still have to tune. So nothing really changed. It's not really adaptive. So let's take a look at the theory, and let's see if, at least in theory, we can do something better than that. Okay? So I said that the only strategy that we know that works in theory is to use some learning rate of the order 1 over square root of t, where t is the number of iterations. So you have this learning rate that is decreasing over time. But you also have that constant eta on top of the learning rate that is the initial one. That is the one that you have to set. Now, the convergence rate of such an algorithm after capital T iteration would be something like this. So there are two parts. The first one is 1 over square root of t. Okay? So it means that after capital T iteration, this thing will become small. You are converging. That thing will converge slowly, but it will converge. And now you have a constant in front of this convergence rate. And the constant depends on this number eta and depends on the norm of the optimal solution. Okay? So this means that if you look at that equation here, you see that basically eta is controlling the trade-off between these two terms. So very easily, the best that this is a weird sentence. I should have written it in a different way. The best learning rate is actually the norm of the optimal solution. This is what you should plug in your learning rate. Now, the problem is that, of course, you don't know the norm of the optimal solution. You're looking for the optimal solution. There is no way you can set that thing. But if you could, this is the optimal convergence rate that you would obtain. So the 1 over square root of t is still the same, but now you get this norm of the optimal solution without the square. So this is what you would gain, setting the thing in the optimal way. And this is not a minor difference. This is a huge difference. That norm might be something like 1,000. And taking the square or not makes a huge difference in the actual convergence of the algorithm. So why we cannot do anything better than this? Are we doomed just to say, OK, this is the best that we can do? We should set learning rate with using some oracle quantities that we don't know. That's it. I will just try all of the learning rates. Sooner or later, I will hit the right one, and that's it. It turns out that, no, there is, at this point, quite a lot of papers on how to do stochastic gradient descent in a completely parameter-free way. This means there are no learning rates to tune. Everything is automatic. So the first paper was by Brendan, that is in Google, and Streeter, that I don't know where he is now, in some other private company, and in which they, for the first time, they proposed an online learning algorithm that was suboptimal, but still it was without any learning rate to tune. So the bound was just slightly suboptimal. There was a logarithmic term, and the right term was square root of the log. That's it. This was the suboptimality. But the key ideas were there. Then I improved it, still with a suboptimal bound, but I was able to extend it to Hilbert spaces. And then I decided to work directly with Brendan in order to obtain optimal bound in Hilbert spaces. So at this point, in Colt 2014, I can say that basically the problem was solved. But the algorithm was more a theoretical one, in the sense that everything was optimal, but the moment that you tried it, it doesn't work. But then here in NIPS 2014, I had a variant of the algorithm in which now the bound is data dependent. You can think about something like going from gradient descent to other grads to have something that actually depends on the data and the behavior of the algorithm. And this was actually the first algorithm that works. It's implemented in VW, the software by John Langford in Microsoft. And you can try it. It's just an option and a command line. It's called Pistol. And you will see that I can assure you 90% of the time the performance will be better than the standard algorithm that it's in VW. And there is nothing to tune. The algorithm is completely automatic. And then there are a bunch of other people that are working on this. I'm very happy that I'm not the only one working on this anymore. And there is also a sort of a parallel line of work on people that worked on learning with experts advice. That it's an online learning setting in which at each time step you have a bunch of experts and you have to choose which one you trust. And then you receive sort of the right decision. And then you keep repeating this game, and you basically have to be as good as the best expert that you didn't know because the sequence of losses is arbitrary. And in that field, there were a bunch of papers that were achieving the same effects that people were achieving on this other line of research, in which the algorithms were, again, completely automatic. Normal edge was the first one in which you take basically the edge algorithm that is sort of the most famous algorithm for this problem, and you remove the learning rate. Everything, again, was completely automatic. The bounds were sort of optimal. And now it turns out that these two things are the same. There is no difference between the algorithms that you would use on optimization, online learning, and just learning with experts. Everything depends on the same trick. Now, the point is that in order to obtain these kind of algorithms, the trick is quite technical and complex. And I think this is also the reason why not many people actually read these papers. And here, but in last year, it was last year? Yeah. Last year, I proposed a different view of this algorithm that is now based on coin betting. So this paper in NIPS 2016, and now a version that it's data dependent of the same trick that will be presented in NIPS this year. I basically view all these algorithms just as a reduction to coin betting. Everything is the same. It's not that I actually changed the results. The results were optimal before and they're optimal now. But now the advantage is that everything is very intuitive. Everything is super clear. It's the design of the algorithm, it's actually makes sense. Before, there was some weird exponent in the middle. It was very difficult to understand what's going on. But now I think it's very clear. And this is what I will present you in the next few slides. OK, so let's start with this coin betting idea. What is coin betting? Coin betting is a game. It's a game between two players. You are the one that wants to gain as much money as possible betting on a coin. Okay? You start with an initial sum of money, let's say $1. And at each round, you decide how much of your money you want to bet on either side of the coin. Then there is only one rule. You cannot borrow money. So let's say that you start with $1 and you say, okay, in the first round, I bet 20 cents that the coin will be head. Then the other player, the environment, will show you the actual outcome of the coin. If you were right, you win money 1-to-1. If you were wrong, you lose money 1-to-1. Okay? It's very simple. And as I said, the aim of the game for you is just that you want to win as much money as possible. Now, when I say you want to win as much money as possible, I say you want to maximize your gain on the sequence of outcomes in which one side of the coin is appearing more often than the other. Okay? If the coin is completely fair, there is nothing that you can do. I mean, it's not really a game in which you can win money. But if you have that one side is slightly biased, you would like to take advantage of it, and you would like to win money. Okay? Now, it turns out that this is a very famous problem. And the first time that people tried to find an optimal strategy for this was in 56 by Kelly that proposed this approach that is called Kelly betting. And it's so famous that you can find it on Wikipedia. There is a Wikipedia page that will describe you this approach. That is very general. It's not just for coin betting. It's super general. But in this case, Kelly betting, when you instantiate it for coin betting, basically says, let's assume that the coin has a probability. Okay, so the probability of, let's say, tail is bigger than 0.5. The coin is slightly biased, and you also know this probability. Okay, you have to make this as two assumptions. The coin is stochastic, and you know the probability. Now, Kelly betting tells you that the optimal strategy is to bet at each round 2 times this probability minus 1 fraction of your money on tail at each round. Okay, it's super simple. And any other strategy asymptotically will do worse. So what does it mean practically? It means that if the probability to get tail is 0.51, okay, it's not fair, but it's just slightly biased, Kelly betting tells you that you should bet 2% of your money at each round. Okay? At each round, you just look at your money, you see how much they are, you take 2%, you bet. In a very blind way. You don't even look at the results. You keep doing this forever. And this is a simulation of what will happen. Basically, your wealth will increase exponentially over time. Okay? It's super simple, and it works. Now, the more the coin is biased, the more the growth rate will increase, but you always win. The only thing that you need is that it doesn't have to be exactly fair. Now, the annoying thing is that you have to assume two things. You have to assume that the coin is stochastic, and the fact that you know the probability. Can we remove these assumptions? Now, let's say that the coin is non-stochastic. It's just a sequence of outcomes. You can think about it as a sequence of 0 and 1s, where 0 is one side of the coin, and 1 is the other side, okay? And this analogy, it's not a random one, because this kind of line of work comes from predicting an arbitrary sequence of 0, 1. This comes in compression. So now you have just a sequence of outcomes of the coin. It's not stochastic anymore. And you still would like to bet a fixed fraction of your money, as before. Okay? And you ask yourself, what's this fixed fraction of my money that I should bet at each round? And now the problem is super simple. You can actually write this thing. You can find the derivative with respect to this fixed fraction and find what's the optimal fixed fraction. And it turns out that it's basically the same as before. But now there is no probability anymore. The only thing that you should do is that, given that the G are the outcomes of the coin that are +1 or -1, you sum these things, you divide it by the total number of rounds, and this is the fraction of money that you should bet at each round. So it's, again, exactly the same strategy as before, but you don't need the coin to be stochastic. You need something else. You need to know in advance how many heads and how many tails you will see in the sequence. Okay, so you remove the one assumption, but you add another one that you should know the future, or at least a bit of information about the future, that it's how many heads and how many tails you will do. But if you know this piece of information, you will have that again. Your winnings will be exponentially growing over time. Everything the same as before. So now we removed the stochasticity, but we add the knowledge of the future. Can we remove also the knowledge of the futures? It turns out that, yes, we can. And this is all known results. I mean, I was just collecting all of them, but this is known. What you should do is that you should use what is called a Krzyzewski-Trofimov estimator. Krzyzewski-Trofimov estimator tells you it's sort of estimating this probability, even if the coin is not stochastic, okay? There is no really meaning in talking about probabilities here, but let's do it because it's simpler. You estimate the probability of the coin looking at the past. And then based on this estimate of the probability, you still use Kelly betting, okay? What the estimator looks like, you cannot just count the number of heads or the number of tails in the past. That would be stupid. Why that? Because let's say that in the first round, you don't do anything, okay? And the outcome of the coin is head. So in the second round, you look at the past and you say, what's the probability of head? Just, maximum likelihood. Probability of head is 1. And so I would bet all my money on head, and I would lose, and that's it. It's finished. The game is finished, okay? So you have to use something a little bit smarter. And so what the Krzyzewski-Trofimov estimator is doing is that you count the number of heads, assuming that heads is the one appearing more often. You add 1/2, and you divide it by the number of rounds plus 1. That's it. It's super simple. Now, the fact that you are adding 1/2 and divided by t plus 1 means that you are adding a little bit of bias in your estimate. It's not a maximum likelihood estimate anymore. There is a little bit of bias, and this bias is going to 0 over time. Okay? This is enough. This is enough to prove that you still bet now. You use Kelly betting. So when you instantiate this thing with the G, this means that you count the number of G in the past. You are at round T. You count the number of G in the past, and you divide by T instead of T minus 1. That's it. The algorithm is still super simple. And what you can show is that if you use this strategy, you will win as much money as knowing the future, but you pay something. How much you pay for the fact that you don't know the future? This factor 2 square root of t. That is nothing, because you are gaining an exponential amount of money if the coin is not fair. So, yes? No, you don't need that. No, you don't need that. You don't need that, because this is just small t. And this is at any capital T, you can stop the game, and this is true. This is true for any capital T at any moment.
I think it's important because if you know how many rounds there are going to be altogether,
Yes.
then you take a certain fraction of that, a small fraction like 10% or 20%.
Yes.
And you see how the odds are, then you know how your coin is buying.
You could do that. But I say that the coin is not stochastic anymore. The coin is just an arbitrary sequence of symbols, 0 and 1s. And this still works. It's not a stochastic coin. So if you use your strategy, what the adversary would do, because this game is all, typically we say that the environment is adversarial. So what the adversary would do is that while you are trying to estimate the probability, would show you a very biased coin. And the moment that you start betting, it will show you the opposite, and you lose all your money. So instead, this strategy works always, anyway. Regardless of the sequence of symbols that you receive, you will win this. Okay? And up to constants, everything is optimal here. The only thing that you can improve is this 2. And another thing that I want to say, Krzyzewski-Trofimov might appear a little bit weird, but maybe some of you knows about the Laplace estimator of count. The Laplace estimator of count is basically the same thing. They both come from the same family of estimator. The Laplace estimator comes from the fact that you put a uniform prior on top of the probability. Krzyzewski-Trofimov comes from a conjugate prior. That's it. And you can actually prove that the Laplace estimator is not as good as the Krzyzewski-Trofimov in the sense that you would get t instead of square root of t. So this is really the right thing. Yes?
Stupid question, but if I change the 1/2, does that change the 2?
No, no. we actually know algorithms that are better in the sense that you improve the 2. And I think the lower bounds, it's 1.4, something like this. And you can go arbitrarily close to it. But then your estimator becomes incredibly complex. And I think it's not worth it overall. Okay, so now, I told you about this game. I told you what's the strategy to win this game. I told you that it doesn't matter if the coin is stochastic or not, you will win it. You always win money in this game, basically. Unless the coin is fair, then there is nothing that you can do. Now, why I should care about it? What's the connection between this and optimization? We started from optimization, remember? Okay, now, this is the key slide of the talk. There will be a proof here. It's the only proof that I will show you. And I will show the connection, how to prove that if you're able to do coin betting, you can also do optimization. Then I will also try to show you a little bit of intuition, but I think it's important to know the math under it. I mean, the intuition was never used to design this algorithm, only the math. The intuition comes after usually. Okay, so the only thing that I need is that you can use any betting strategy you like. It doesn't matter. The reduction is sort of general. The only thing that I need to assume is that whatever strategy you use, it guarantees you that the amount of money that you win on any arbitrary sequence of GT is some function of the sum of the GT, okay? Any function you like. So for example, this means that if we use the KT estimator, the Krzyzewski-Trofim estimator, the function h will be of this form. It's that exponential thing divided by square root of t, okay? That's it. You just need to know that this function exists. Then you can use any strategy you like if you don't like Krzyzewski. Now, let's say that we want to minimize the function absolute value of w minus 10. That is exactly the function that I showed you in the first slides. It's a one-dimensional function. And also, and there's also a very nice property that the gradients, I should say subgradients, but let's say gradients, the gradients are exactly +1 and -1. So the gradients are exactly, you can look at them as just outcomes of a coin. So we have the outcomes. We just need another thing. So the dollars that we bet at each time, that is given by the strategy tells us bet something, are the W that you try. So each time the betting strategy will tell you bet 20 cents. That means the W that we try is 0.2, right? We tried 0.2, we receive a gradient, and the gradient is nothing else than the outcome of the coin. Then you win or lose money, and the betting strategy in the next round will tell you, bet something else, and that is the W that you try, and so on. Now, my claim is the average of the bets that you do over time will converge to the minimizer of the function. Okay? Now, let's prove it. It's super simple. Okay, so f is the function that we want to minimize, and this is the average of the bets. W is the bets. Remember the money that we bet each time. And W has a sign, because each time I bet money on one side or the other, the two sides are +1 or -1, so this is amount of money multiplied by the side, okay? So this is a real number. I take the average of this thing, and this is f in the optimal solution. So I want this difference to go to 0, right? In that case, that will converge. So the first thing that I do is that I use Jensen. I use Jensen inequality to take this expectation, this is an empirical expectation, and I bring it outside. Okay? Easy. Now, next step, convexity, the property of the gradients. I take the functions here, and I can substitute them with the gradient. It's just because for every convex function, you can construct a linear lower bound to the function that is exactly that. Okay? So the function disappeared. Now you have the gradients, Wt and W star. Now, I look at this thing. I look at GT, Wt. Remember, GT is the outcome of the coin, and Wt is the amount of money that I bet. This sum is the amount of money at the end of the game that I have, because each time I win or lose something, and this is the sum of money. And I know from my betting strategy that that quantity is at least h, some function h of the sum of the GT. That was my assumption. So I go here, and I substitute these with h of the sum of the GT. Okay, I upper bound it. Okay, there is an additional term because I have to start from something. So I start with $1. This is the total money, and this is just the net money that I am winning at the end of the game. Okay, and this is a minor point. Now I look at this thing, and I looked at here there is the sum of the GT, and here there is the sum of the GT. So I say, okay, you know what? I want to remove the sum of the GT. I just take the maximum with respect to a variable v of this quantity here and this quantity here. Okay, and I can upper bound this thing. Now we are done. If I stare at this thing long enough, I will see that this is the definition. This is really the definition of the functional conjugate of h. The functional conjugate of a function in one dimension is defined like this. So it's finished. Now I go back to the first thing and it says the average of my bets minus the function in the optimum is less than something that it's 1 over t. So I am converging. And I am converging to something that depends on what? Depends on the functional conjugate of the function h of the betting strategy evaluating the optimal solution. This means that the better is my betting strategy, the smaller is h star, the better is the convergence of the algorithm. Now, why these things? It's nice because I cannot just now use it. This is the actual algorithm that I would use. I have the GT are just the subgradient minus the subgradient of some function in the WT that I try each time. And let's assume, as I did in the slide before, that the gradients are just +1 or -1 because I need them to be a coin. The actual algorithm that I would implement is this one. WT is equal to what? Kelly-Betty strategy applied over the Krejcicki-Trofimov estimator that says you just count in the past divided by the number of rounds +1, and this is the fraction of money that you bet multiplied by the wealth. The wealth is nothing else than this, so this is the actual algorithm. This is gradient descent. And if you implement that, and you plug in the bound before, you just have to calculate h star, and h star turns out to be this thing. So you have that. You will converge at the optimum at a rate that now is optimal. There is no square here. And there is nothing to tune. There is no learning rate, no eta, nothing. I mean, the algorithm is there. If you can implement SGD, you can also implement that thing. Yes?
I'm going to ask a dumb question. I don't understand what, I understand that for the landscape of the function,
Yes.
the only gradients are +1 and -1.
Yes,
But I don't understand what the sequence of +1s and -1s that corresponds to the point clips comes from. Where's that sequence coming from?
Oh, it's just the gradients. The gradients that you observe. +1 and -1, you observe these gradients.
So it's not a predefined.
No, 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 no.
Okay.
No, no, no.
Okay.
That's another question. Could you tune the amount of money that you start with?
Yes.
What is that? That'll just manifest itself in the constant that you're having, or?
It appears, there is a tilde here, though this means that there is a logarithm. It will appear in a logarithm, and outside of the logarithm as an additive factor. So it counts nothing. It doesn't matter, basically. Now, the one limitation here is that I assume that the gradients are exactly +1 or -1. And I am in 1D, everything in 1D. So it turns out that I can use exactly the same algorithm, nothing changed, and I can just assume that now the gradients are between -1 and 1. And everything works. And what's the key idea on the proof? The key idea is that the worst gradient that I can receive, because this is an online learning proof, so I always say everything is adversarial, the sequence is adversarial, anything can happen. The worst gradients that I receive are anyway +1 or -1. So if the algorithm works in this case, it will work in any other case in between. Okay?
So what does worst mean?
Worse in the sense that the sequence of GT is arbitrary. Sequence of GT is arbitrary, and every time I ask myself, what's the thing that the adversary could do that would hurt me the most? And it turns out that he should always play one of these two.
But what if your service is
then it's fine.
The gradients are 0.
It's
then
fine.
You're not moving.
If your gradient is 0, you arrive at the optimal. So you are done.
No. I mean, if it's flat and then
Then it's non-convex.
okay. Got it.
Okay, now, there is still one problem. Everything is, yes.
We were counting the number of heads, so if it's a fraction, like what do we count that?
This is the algorithm. It's still this. You just sum the GT. Now they are not +1 or -1 anymore. They are just numbers. You just sum them. I think it will work. Now, the remaining problem is that everything in 1D. But it turns out that, again, you can extend this thing to Hilbert spaces. So infinite number of dimensions, everything works. Now, the coin is not a coin anymore. It's a vector. And you just have to assume that the norm of this gradient is less than something. It doesn't have to be 1, less than something. So the function is Lipschitz. Everything is the same as before. Now you don't average number anymore. You average vectors. But it's still doable. And this thing that was a product before, now it's an inner product. And the proof basically goes through the fact that, again, you look at the worst direction that you can receive. So you say, OK, now what's the worst thing that can happen? And it turns out that you can characterize the direction. So you know the direction. Once you know the direction, you're on a line. And then once you're on the line, you say, what's on this line the worst value that I can get? +1 or -1? And then you're on a coin. And everything works out. So the proof is quite technical, but this is basically the intuition of why it works. And the final thing that I want to show, that I want to stress, is that the algorithm is super simple. Super simple. The bound is optimal up to logarithmic term that you cannot remove them anyway because there is a lower bound that says that they should be there. And that's it. OK, now, this is a very simple algorithm, but there are a couple of limitations. So this is just applying, Krzyzewski-Trofimov as yes.
Maybe a dumb question.
Yes.
So should I think of this thing in the parentheses as like the learning rates?
No.
I'm not thinking about that.
No.
Because because I'm trying to write it like a.
I know. Yeah, you get
Yeah.
this is more FTRL. It's not mirror descent.
Okay.
In FTRL, you always have the sum of the gradients,
Yeah.
and you do some transformation on top of it. And this is the kind of transformation that you do. If you want to look at the learning rate, FTRL with the usual learning rate would be sum of the gradient divided by square root of t, small t. So you can look at this thing divided by square root of t as the effective learning rate. Yes, that is reasonable. But it's just, it's just,
Some other thing.
yeah, I mean, I don't think it's really that. OK, now, one problem is that the entire thing is based on Krzyzewski-Trofimov. That was the key idea. I use Krzyzewski-Trofimov because, it's optimal, everything. It's super easy. I just have to sum the GT and divide it by t, and that's it. This was the key thing here. This is the fraction that I bet. But I can use anything else there. There is no reason why I should use Krzyzewski-Trofimov, and maybe I can use something better. I told you that Krzyzewski-Trofimov is optimal in the sense that you cannot improve that. But it was designed for coins. These are not coins anymore. Now these are something different. Even in the 1D case, you have a range. And you can very easily prove that Krzyzewski-Trofimov is not optimal there anymore. It's optimal only if you are exactly +1 or -1. The theorem still works, but it's not optimal anymore. And the other thing is that I would like, the final aim was that I wanted to try this thing on deep learning. And the reason is that every time I was going around presenting this work, people were telling me, yeah, it's nice, but does it work on deep learning? I said, hey, you should try it. And I say, oh, yeah, I'll do it. Nobody did it. So I decided to do it by myself. And let me first give you an intuition. I forgot about this slide. I promised you the intuition of what the algorithm is doing. So if we apply that algorithm on this function, what the algorithm will do is the following. You start from 0, OK? First round, you don't bet anything, because it's very smart not to bet anything, because you don't know what will happen, OK? You can start from any point. It doesn't matter, but still, let's start from 0. Then you observe the first gradient. The first gradient is the coin, right? So the first gradient is -1. So you know that in the next round, you will bet on the negative direction of the gradient. So you will move in the positive direction, and you will bet some money. And you will be right, because the next gradient, it's also minus 1. And again, minus 1, minus 1, minus 1. What does it mean? That you get this sequence of minus 1, and you are winning more and more and more. And so you make more and more money. You make an exponential amount of money. So you move exponentially fast from 0 to the optimum. Once you are here, at this point, you again bet that the next outcome will be minus 1, and you are wrong, because now you get a gradient of different sign. So here you lose a lot of money, because you bet a lot. You were really, really confident about it. You lose a lot of money, and you go back there. And then you, again, will climb up again in this region, and the average of your bets will converge at the optimal rate. So what you can do is that you can plot, another way to look at this is to plot what the quantity that I was telling you before, that effective learning rate. And you can see what that effective learning rate is doing, and it's doing something very nice. When I am really far from the optimum, the learning rate is far. It's oscillating, but it's far. It's really big. Because I'm far from the optimum, I want to go really, really quickly in the area that is interesting. Once I am there, I should decrease the learning rate. Otherwise, I will never converge. But the entire thing is automatic. You know, I never looked at this thing before, I think, a few months ago. Because, you know, the math just tells you that everything is optimal. So it should do the optimal thing. And then I said, OK, let me see what it's actually doing. It's doing something that also makes sense from an intuitive point of view. Yes? Right, but they don't know it. So AutoGrad is doing it in a blind way. It will just, you know, in that function, it will just do 1 over square root of t. That's it. No matter what happens, it will always be 1 over square root of t. This algorithm then it will increase exponentially the learning rate. It's very different if you think about it. Increase exponentially. Once I start getting gradients that are alternating sign, I decrease. No, it will start losing money. Once I start receiving gradients that are opposite sign, so plus 1, plus 1, plus 1, minus 1, I will never win money in that situation because the coin becomes fair. Once the coin is fair in that situation, there is nothing to win. The probability will go to 0.5, the estimate of the probability, and my actual W will converge to the right thing.
So is there a version? So here you're looking at changes in the gradient.
Yes.
That
Yes,
are
right,
informing
right,
whether your
right.
steps
Somehow,
keep
yes.
growing or getting
Yes.
smaller. What about looking at the loss and just saying,
Oh,
saying, hey, you know, I've taken a couple of steps in this direction. The loss is
right.
increasing dramatically.
Right.
Let's make an even bigger step until the loss stops
Okay.
increasing.
Okay, this is a good point.
And
Yes.
then reduce step size
Right.
exponentially until the loss is decreasing.
Right. It's a good point. I never thought about it. I think the main problem is that typically people don't want to evaluate the function. It's kind of expensive. Gradients, even the gradients, we don't evaluate the gradients. We evaluate a stochastic version of the gradient. Evaluating the function itself, we will not.
Right.
Nobody would do it. We would evaluate
the
an.
batch loss.
Yeah, we would.
The loss on the batch.
Yeah, we would evaluate just loss on the batch, and then yeah, it could work. I don't know. It's a good idea. Yes. Okay, so let me tell you. Okay, I should be able to do it. So how to make this work for deep learning? So we go through a couple of steps. The first one is that I want learning rates that are different for each coordinate, because this is what everybody does in deep learning, at least till the latest SNPs by Nati Cerebro. I don't know how many read it. Anyway, and this is super easy. You just have one coin for each coordinate. The proof goes through. It's trivial. Now, the other thing that I wanted is that I wanted faster convergence when the gradients are sparse, because this is something that is happening a lot in deep learning because you get this truncation that makes a lot of gradients 0. Now, if you look at the algorithm here, every time you receive a g that is 0, you still divide it by t, so the time will pass. But intuitively, you should not do anything. You know, a gradient of 0, it's like that round didn't happen. But the time will not know about it because it's time. So the intuitive idea is that to substitute this time here to something that is data dependent, that depends on the actual G that I observed. This is like in undergrad. It comes from there. And so what I did is that you start from this strategy, and you substitute with something else that now is data dependent. So you take this time, and you substitute it with the sum of the absolute value of the gradient. So now if you receive the gradient that is 0, nothing will change. The wealth will not change. This will not change. This will not change. And you should get a faster convergence in this case, and you will see from the bound that this happens. The sigma here is a sigmoid, and it comes from the theory. I mean, in the proof, at a certain point, if you don't put the sigmoid around this thing, nothing will work. So it's there just from the theory. Now, if you do these two changes, you get that this is the kind of convergence guarantee that you can obtain for convex and quasi-convex functions. Now, it can seem a little bit scary, so let's look at something different. Let's look at the bound of Adagrad. This is the bound of Adagrad, the one that you would obtain with a learning rate eta that small number that you still have to tune. Now, what's the difference between these two? There are two terms. In this one, it's just the sum of the gradient squared divided by t, and then the square root. In my case, it's the sum of the absolute value of the gradient multiplied by the worst gradient. So this term is slightly worse, slightly worse. In upcoming work, I improved this term, and now they're exactly the same, but it doesn't matter at this point. This is the most important term that I was carrying before, that is the one that depends on the learning rate, that I don't have anymore this learning rate. So if in Adagrad, you tune this eta for each single coordinate that you have. So you have a deep network, you tune with 1 million weights, you tune 1 million weights. What you would obtain is my bound. Yes? Or even quasi-convex. No, but you know, I cannot prove anything in that case. Nobody can. So you know, the idea was, let's try to prove it at least in a convex case, and let's try empirically if it works. And then I'll tell you in one slide that it doesn't. So I mean, the story is not finished. So the point was that, again, you don't have a learning rate, and what you obtain, something as good as Adagrad, but you know, the optimally tuned Adagrad that nobody can do anyway. Okay, now I tried it on deep learning, and it doesn't work. It doesn't work at all, and the reason it's simple. Convex functions are kind of special. You can take arbitrarily far jumps, and it doesn't matter. The function is still convex. The gradient will always tell you, go back to the right direction, and it will point you to the minimum. Everything is fine. For deep learning, this is completely false. Deep learning are initialized in a very special way. The noise has to be from a certain distribution with a certain variance. That is really important. It's not a minor detail. That will put you in a nice spot to start your optimization. The moment that you do the first jump and you are too far from that initialization, you will never, ever recover. You will end up in another point that is now it's a bad initialization, and that's it. The algorithm, the network will never learn anything. Okay? So it's super critical that in deep learning, the first steps are small. And this is an empirical thing. I mean, I don't have an explanation for it. It just happens. You can see it. You can take Adagrad. You can put a learning rate of 1, and you will see. You can plot the training error step by step. You will see that in the very first step, it will go to a point. It will never move. The training error will never decrease, basically. Okay? So I had to change the algorithm, and now from now on, I don't have it here anymore. It's just things that I did because otherwise it doesn't work. So that is the update rule that I was using. So the first thing, there are a number of problems. This is one. The other one is that I need to know the maximum gradient for each coordinate. Again, this is impossible in deep learning. The range of the gradients is changing over time, and it's different for each layer of the network for the vanishing gradients. There are all sorts of problems. So that part was easy. I just say, okay, I don't know L. I just estimate it. I start from 0. Every time I observe something that is bigger, I update my estimate of the biggest gradient. That's it. Now, this thing will make also the fact that LR estimate will make the wealth become negative. At a certain moment, the betting algorithm will lose all the money. This will completely destroy the algorithm. So in that case, I just say the wealth cannot be negative. The moment that you lose all the money, I give you $1 back and you start again. Then I remove the sigmoid because it was coming from the theory, but it doesn't help in practice. And then I make sure that the first steps are small. Okay? These are critical changes. And so this is the actual algorithm now I use. So L is estimated over time. The wealth, it's always a minimum wealth, cannot never be less than, this is basically the dollar. And there is no sigmoid. And the learning rate here, it's never, I mean, this is not a learning rate. This fraction here is never too big because there is a maximum of 2 terms. And there is this 100 times the maximum gradient here. So that means at the beginning, the sum of the gradients is just too small. And this fraction could become really big as 1/2. So this means that the jump that I do is something like 1/2 in one direction or in the other. And I just say you cannot make, the steps cannot be actually bigger than 1/100. That's it. So the first steps are small. And if you remove that thing, nothing will work. Now 100 was just, you know, I didn't tune it. It's just 100, that's it. It works all the time. Okay. Now there is more, but I think I'll skip this slide. Let me show you how this works. So what I did was to try different architecture, different data sets, to implement my algorithm in TensorFlow. By the way, the code is online, it's on my GitHub. If you want to try it, it's just, you have to change one line in your TensorFlow code because you just changed the optimizer. And I compared training error and test error with the different number of epochs of, you know, my algorithm, that is called COCO, by the way, that is the red line, compared to what is considered the state of the art in deep learning. So AdaGrad, RMS Prop, AdaDelta, and Adam, that is sort of the most used one. Now, I cannot claim, given that I cannot claim any convergence because I did the change and the function is non-convex, but also I cannot say anything on the test error. At this point, nobody can say anything on test error. I mean, there is a lot of research on if they will converge to a local minima or just to a critical point, you know, all these kind of small details on the training error. But on test error, we really don't know anything. So we just know that it works. And so I cannot say anything there. But it turns out that there is a very strong correlation in all my experience between training error and test error. So if the training error is good, you can expect the test error to be good. And so you can see that my algorithm is beating all the others. In terms of convergence rate. I don't have anything to tune. The others, for the others, I use sort of what is called the standard, you know, parameters, because all the others, they claim to be automatic. This is what they claim. Then it's not true. They still have small parameters, and you still have to tune them, you know, in order to get optimal performance. But if you use them out of the box, I just crash all of them, basically. And this was MNIST, full connected network. Then this is again MNIST, convolutional neural network this time, a very standard architecture. And again, it's always more or less the same. My algorithm is the same or better than the best of all the others. Training error, it's always good. Test error, it seems to be good and, you know, follow more or less the trend of the training error. Then another data set that was CFAR10. This is, again, a computer vision data set. It's more complex than MNIST. Here we get the performance is very close to the one of AdaDelta and AdaGrad, slightly better. Adam is incredibly unstable on this data set. And I mean, if you look at the algorithm of Adam, there is actually no reason why it should be stable. There is actually no proof of convergence for the setting, not even in the convex case. Adam, it's known to converge only if the learning rate will go to 0. And it's not how it is used. The learning rate of Adam is fixed, and it's a magic number. It's 0.0001. And that has to be always. So it can be the case that it will oscillate, because if you look at the algorithm, there is no reason why it should not oscillate. And the last experiment that I will show you is something completely different. This is now a recurrent neural network. And now the task is to predict the next word given the past. This is Pentry Bank dataset. And the network that I used was just straight from a classic paper. So everything, it's, I didn't invent these experiments. And again, you have that basically my algorithm is on par with Adam, slightly better than undergrad. And on test error, this is the first time in which all of them are overfitting. Because again, we are not saying anything about the test error. You should basically, at this point, early stop all of them, and you would obtain the same performance on test for all of them. And I think it's important to show something that it's not the usual convolutional neural network and the image computer vision dataset, to show you that this is an optimization algorithm. It should always work. It doesn't matter what you optimize. I mean, there is nothing specific to convolutional neural network. I mean, if you cannot optimize that, you should always be able to optimize recurrent neural network, and it seems to work pretty well. Okay, so I'm done. I'm probably a bit late. So if you want to forget everything about this talk, I would like you to remember just one sentence. That is, learning rate in stochastic gradient descent for Lipschitz function quasi-convex are not necessary. Okay? You don't have to use coin betting. This is just what I propose. I like it. I think it's very elegant in a way. But the point of this paper is that it's possible to do better. There exists a class of algorithms that is not using a learning rate, and it's optimal. So every time you are using actually something that has a learning rate, or you are trying to design an algorithm that has a learning rate, you should know that you are doing something very suboptimal. It's like designing a sorting algorithm that for some magic reason now has a parameter. People would tell you, why should I use that when can I use a quick sort? Okay? And then there is a bunch of different things that you can do, that SGD, GD, learning with experts. I didn't tell you something about SVM, but you can reduce also the training of an SVM with kernels to betting on a coin. And you will obtain a lot of guarantees with respect to the decay of the eigenvalues of the kernel matrix. It's something from non-parametric statistics. But again, you gain basically the same adaptivity. Here you remove the learning rate. In the case of the SVM, you remove the regularization parameter, and you are optimal with respect to that. And these betting algorithms, I found them extremely easy to design in the end. I mean, KT is just count over the past and be a little bit smart about that. There are no parameters to tune in this algorithm. And most of the time, you will obtain an algorithm at the end of the day, in the reduction is optimal. So in future work, what I'm doing these days is that I'm working with Ashok, that won the best paper award in Colt this year. It's a super smart guy in Stanford that basically, and we are basically extending this thing to Banach spaces. So I can now reduce even optimization in Banach spaces, not only Hilbert spaces, to betting on a single coin. And the other thing that I would like to do, and I still don't have a clear idea how to do that, is can I sort of fuse this idea of coin betting with Newton algorithms? So till here, I didn't assume anything about the curvature. This is no smooth optimization. This is very nasty function. But if I know that the function is curved, there is some curvature, I would like to use it. So can I take the best of the two worlds? Can I have an algorithm that at the beginning is using some coin betting idea to go very quickly to the area where there is the optimum, and then there I would start using the curvature. Okay, so that's it. Thanks for your attention.
Is there time for questions? If anybody has any more?
Yes.
So for deep learning on the, I mean the version you use for deep learning, you say the learning rate still usually increase.
Yes, it's the same.
Then is it then you just at some point increase and become too large?
Right. But there is that small thing that I added that at the beginning cannot be too fast in a way. During the algorithm, it cannot be too fast. I mean that that max thing will prevent any bad behavior of the algorithm. in the 1D case or the Hilbert case? Here. Okay, so the proof, these kind of proofs, there are online learning proofs. So they are stronger than these. I can prove something that's actually stronger than this. This is a convergence guarantee. What you actually prove is that the regret of this algorithm is of the order of square root of t. So the regret of the algorithm is something that says, no matter what is the sequence of the GT, you are never too bad compared to W star. But it doesn't have to come to from a function. It's any sequence of the GT. Okay, this is
So it's not necessarily this way.
no, but the point is that in that kind of proofs, the proof works in this way. At each every time you say, what's the worst thing that can happen? And the worst thing that can happen is this. So it doesn't have to be exactly -1 or 1. It has to be a range, and you have to know the range in advance. So it's minus L, L. Okay. And when you go through the proof, you will realize that the worst thing that can happen is that you get exactly plus L or minus L. And then you build the algorithm in a way that is resistant to that case. All the other cases are easier.
So there are tricks like gradient clipping for training these networks.
Sure.
So you need to do that.
No, the last experiment said gradient clipping just because this was the setting in the original paper they were using it. We reproduced exactly what was in the original paper. And so in these experiments, there is gradient clipping. But there is no need to use it. Yes?
This is most likely a naive question, but I guess some other methods such as regular gradient descent always has on their 9 finds the local minima instead of the global one.
Right.
So this also has the same.
Yes.
Thank you. Yeah, like I said, it's very naive.
No, but that is impossible. I mean, it's unless we assume something very specific about the distribution, it's just impossible to do that in a time that is not exponential in dimension.